Hi, this is Mr. Barron, and this is the third in the series of the nuclear chemistry lectures. Now we're going to be talking about the actual applications of nuclear chemistry beyond just using half-lives to date how old things are. Let's first start off with the difference between nuclear reactions versus chemical reactions. Remember, nuclear chemistry only has to study the nucleus, so it only involves changes in the nucleus. Chemical reactions only involve changes with electrons, and that changes how things are bonded. Nuclear reactions have much more energy released than chemical reactions. How much? Think nuclear explosions. So where does all that energy come from in a nuclear reaction? Well, it actually comes from this thing called the nuclear binding energy, otherwise referred to in this class as the nuclear force. And there's many different types of nuclear forces. But we're not going to get into the details. We're just going to briefly touch on where this energy comes from. So there's a lot of nuclear forces that are in the nucleus on this picture on the left, holding those protons together in the nucleus. See, those protons want to be pushed apart because they're like charges. They're positive and positive. So there's these additional nuclear forces holding the nucleus together. The energy released when is released when a nucleus is formed or broken apart. This is just a simplification of it, of course. It's a lot of energy to counteract those protons repelling. You can calculate that energy because a little bit of mass is lost when the nucleus breaks apart or is formed. And this is called Einstein's special theory of relativity, and you guys know it as E equals mc squared. And by that mass change, you can measure how much energy was released. So let's talk about one of the classic nuclear reactions that we use for nuclear power plants. This is called the fission reaction. What happens is a stray neutron is absorbed by uranium, becomes unstable, and then fissions apart into two daughter products plus some additional neutrons. Actually, it should technically be 3 neutrons. When this fission occurs, then those neutrons can go on to strike other uranium atoms and split apart as well. This is the accurate equation describing what happens is shown right here, where it shows uranium fissioning apart into krypton, into barium, and 3 additional neutrons. So, what happens to those additional neutrons? Well, they can go and strike other uranium atoms. So each of these red dots, which are uranium, each time they fission apart, it releases energy. Notice that you start off releasing a little bit of energy, then all of a sudden you end up with this chain reaction of all the uranium atoms being fissioned apart almost simultaneously, and it releases an enormous amount of energy all at the same time. This is what we call a nuclear fission chain reaction. So the difference between a bomb and a power plant is that in a bomb, it's an uncontrolled fission chain reaction. In a power plant, it's a controlled fission chain reaction, and the uranium used for a power plant cannot be made to create an explosion, a nuclear explosion in the same sense, but can cause the reactor to generate too much heat and melt down. So this is actually what uranium looks like on the left when you dig it out of the ground. It's often referred to as yellow cake. On the right, that's the processed uranium that's actually used in a power plant. Notice the person's holding it. And they're holding it with a glove, but uranium isn't, the uranium used in a power plant needs those neutrons for it to actually start generating heat. That's why a person's able to hold it. So how does a power plant work? Well, look in the yellow. The yellow is where all of the nuclear energy is located. So you have the reactor, and you have water going over the uranium that's fissioning apart, releasing energy. It heats up that water, and basically you can see it goes through another pipe inside another container where there's water, and it boils that water, changes it into steam. The steam turns a turbine, and then that actually produces the electricity. You cool down the steam, changes back into water, and then it can be heated over once again. There are these control rods that are actually used to control the chain reaction. Now, control rods absorb neutrons. That prevents the chain reaction from getting out of control. If you don't have those control rods, then it can very much get out of control. This is an example of what happens when you lose control of the nuclear fission chain reaction. This is a picture of what happened to a nuclear reactor that's located in Ukraine. This happened in the 80s. It was in the former Soviet Union, and notice there's no containment concrete around the reactor, and it melted down. It was a nuclear meltdown, and that meltdown caused a lot of the radioactive materials used to generate the electricity to be dispersed into the atmosphere, killed a bunch of people. It was an explosion, but notice not a nuclear explosion, not like an atomic bomb explosion. And if it was, then there wouldn't be anything left. But there was still an explosion because a lot of heat was generated, and unfortunately, a lot of people were killed, and a lot of radiation was spread into the environment, and everyone had to evacuate the town that this power plant is in. So that's one of the major downsides. We have not had a nuclear meltdown like this in our country. Now, nuclear fission and power. Currently, about 103 nuclear power plants are in the U.S., and there's about 435 worldwide. That was at the time that I made this PowerPoint. 17% of the world's energy comes from nuclear energy, and here's some lists of countries in terms of the percentage of the electricity that they get from nuclear power. Notice we're not at the top. Most of Europe is actually using nuclear energy. We get about 20% of our electricity from nuclear energy. Now, what do we do with the byproducts, the daughter products left over after things have fissioned apart? Well, this is a picture of one of the proposed sites to place nuclear waste. You obviously want to keep the nuclear waste stored for a long time because it takes a long time until it decays down into stable nuclei that's safe and not radioactive. Currently, we're storing all of our nuclear waste in the area that we keep the nuclear power plants. We haven't developed a central storage system. You've heard possibly in the news about an area in Nevada called Yucca Mountain, where we've proposed to tunnel out the mountain where it's very dry, very little seismic activity to disturb the nuclear waste, and we would store it there. Unfortunately, we haven't come into any decisions at all about any central place or a good location to store most of our nuclear waste. Now, let's talk once again about a fission chain reaction. There is this thing called critical mass, and that's the mass of fissionable material needed for the chain reaction to begin. That's when you actually end up with a type of reaction that would create a nuclear explosion. All right, so how long will it take for a nuclear waste to become safe? Eventually, all radioactive waste decays into non-radioactive elements. For waste being produced today, it will be centuries before all atoms are stable and stop decaying. How long depends on the half-life of the nuclear waste produced. So again, fission. The opposite would be fusion. Now, fission versus fusion. Fusion is when you have light nuclei combining together to form a heavier nucleus. So here's an example of a helium atom being formed by hydrogen. Fission, of course, are atoms breaking apart. Now, there is a nuclear fusion video that we watch in class that shows a lot of animations explaining the difference between the two processes. This is the equation that's been proposed for the type of reactors that are being tested right now that are nuclear fusion reactors, and it's when you have deuterium, which is an isotope of hydrogen, combining with tritium to form the helium nucleus. This occurs in the sun and other stars, and mass is lost when you combine these two, and it's converted into energy, and you can get energy out of this process just like with fission. So this is the proposed equation that you saw in the video of fusion. So the mass that's lost between what you started with and what you are left over with is converted to energy, and a fraction of that lost mass is converted into all of the energy that's needed to possibly generate electricity. Nevertheless, the fusion energy released from just about a gram of deuterium and tritium equals the energy of about 2,400 gallons of oil. This is an inside picture of a tokamak fusion reactor located in San Diego. There's another picture of it. And there's another picture of it. In terms of energy release comparisons per nuclei, fusion releases a lot more energy than chemical reactions, combustion by burning things like fossil fuels. Fission, a little bit less, but pretty close to fusion. Now, radioisotopes at work. Let's talk about human-made isotopes. New elements or new isotopes of known elements are produced by bombarding an atom with particles. An example of this is taking uranium and a neutron, combining them together and forming a new element or a new atom of uranium, which is an isotope. You can also take plutonium, collide it with a alpha particle, and you can get curium. So one of the cool things is that we can actually produce elements that don't exist naturally. All elements above uranium are man-made by these things called particle accelerators. Here's a picture of one in Stanford. So when you collide these particles, sometimes the particles basically stick, and then you end up with a larger atom, and that's how we created atoms that are much heavier on the periodic table than what we found naturally existing on our planet. Here's another one. This is a whole different type of research where they're studying the parts that actually make up the subatomic particles that make up atoms. This is the Stern facility in France and Switzerland. It actually crosses the border. Now, nuclear medicine imaging. We actually use radioisotopes to be able to identify glands and be able to get images out of our body. Another application is treating cancer with high energy electromagnetic radiation, ionizing radiation to kill tumors. Also, we treat foods occasionally with irradiation, which is from gamma rays that come from cobalt-60 or cesium-137. Irradiated milk, believe it or not, can have a shelf life of 3 months without refrigeration. So there's a lot of cool applications for radiation for killing things that can be harmful to us. And the USDA has approved irradiation of meats and eggs, and you sometimes see a sticker that identifies foods that have been irradiated to make them more safe. Now, if you guys have any other questions, shoot me an email. Otherwise, this is just a PowerPoint going over the main ideas of how we can apply nuclear chemistry into a lot of different fields and develop technologies that can help generate electricity, kill tumors, and also make our food more safe.